Hi, and welcome to the General Physics 2 online lecture on capacitors. Capacitors are showing up at the end of our electrostatics unit, and we're going to briefly describe their electrical properties, but we will see capacitors again when we work in our electric circuits unit, because there we'll talk about what happens when you insert a capacitor into an electric circuit. If you've ever torn apart any electronic device, an old computer, something of that nature, you may have noticed that among the many components in there are devices that look something like one of these in the picture. These are in fact all types of capacitors torn out of various devices, and they all have one thing in common, however, in that you'll notice each one has two wires or two leads connected to it in some fashion, though I guess these at the top, it's not so obvious where those two connections are. And a capacitor is a device that stores electrical charge, and it stores, therefore, electrical energy. And so our goal in this discussion is to build a little bit of understanding about how a capacitor stores that charge and why that would mean that the capacitor stores some energy in the process. Most generally, a capacitor is simply two conducting materials that have opposite charges that are near to each other. So in the diagram that just came in here, here's some region, some sort of material that I've charged positively. Here's some sort of material that I've charged negatively. There would exist an electric field between those two charged objects, and so that's sketched here in the diagram. This device and this arrangement would actually store electrical charge. If we then used a conductor to connect the positive region to the negative region, then we would actually get a flow of charge between those two until both of them became electrically neutral. We usually start, however, rather than this generic amorphous blob, by talking about a parallel plate capacitor. And so here's a picture of a parallel plate capacitor. Again, I have two sheets of conducting material. In this case, they're both rectangular and they both have the same area. These are not necessary conditions to make a capacitor, but they're easier to do the analysis on if you make them equal in size to each other. So in this diagram, we're saying that the bottom side of the top plate has a positive charge and the top side of the bottom plate has a negative charge. Again, if the top plate is positively charged and the bottom plate is negatively charged, those charges will exert forces on each other and they'll pull the charges towards each other as close as they can get. Well, as close as they can get is the inside surface of this capacitor. There's some separation distance between the plates in that capacitor, and in order for it to store charge, you have to establish an electric potential difference between those two plates. And as you'll see in the simulator we're going to play with shortly, essentially what you have to do to charge a capacitor is pull an electron off of the plate that's going to become positive and somehow send it down to the opposite plate. So then you leave one plate positive because you've removed an electron from it, and you make the other plate negative because you've added an extra electron to it. And you keep doing that process until the system is holding as much charge as it can given its current arrangement. So capacitance is defined as the amount of stored charge divided by the potential difference between the plates. And capacitance, as we'll see in a little bit, is a fixed value based on the physical characteristics of this system. And it tells you how much charge this system can store for a given amount of potential difference between these plates. So if I have a certain amount of capacitance in this system, if my potential difference between the plates is 0, that means I'm storing no charge. But as I increase the potential difference between those two plates, I increase the amount of charge that's stored on that system. Shorthand, capacitance is going to get a capital C, perhaps slightly unfortunately, since we've been using capital C as a unit to express coulombs, the unit of charge, but here this is standing for capacitance as a variable. Q is our unit for charge, and then a potential difference we write with a delta V. So there are three questions on these slides that just going to ask for your intuition about. And again, I would encourage you to jot down what you think the answer is in each of these situations. And then we're going to play around with a simulator that will hopefully allow us to visualize what the answers are to these three scenarios. So, in order to charge a capacitor, I have to connect those two conducting plates to some sort of power supply. So I've drawn a battery right here. And you can think of a battery in this situation as a charge pump. It's going to pull electrons off of the top plate, send them through this system, and deposit them on the bottom plate, and that will make the top plate become positive and the bottom plate become negative. And it'll keep doing that process until it can no longer add additional charge to the bottom plate. The way I think about this is, okay, it's fairly easy for whatever this pump is to pull one electron off of the top plate and dump it on the bottom plate. But the second electron that it pulls off the top plate and tries to deposit on the bottom plate is a little bit harder to do because we previously added an extra electron to the bottom plate, so we made that bottom plate slightly negative. And as you know, negative repels other negatives, so it's a little bit harder to put that second electron on the plate. It gets even harder to put the third electron on the plate, the fourth, the fifth, and it's increasing in difficulty. And at some point, the battery no longer provides enough energy to pack additional charges onto that bottom plate, additional electrons, and at that point the capacitor is considered to be fully charged for the arrangement that it's currently in. Alright, so three questions. If we increase the area of the plates, so if I took those same plates from my scenario at the top, but I made them bigger, say I doubled the area of each one of them, what would that do to the capacitance, the ability to store charge? Would you think that the capacitance should increase, the capacitance should decrease, or the capacitance should remain the same? Again, at this stage, I'm not answering these questions. I just want you to get down your thoughts about these three scenarios, and then we'll answer them all via the simulator. What if we took those same plates and we put them back to their original size, but instead of changing the size of the plates, we changed the distance between the plates? So we changed the separation between the plates. What would that do to the capacitance? Does that increase the capacitance, decrease the capacitance, or make the capacitance remain the same? And the third scenario, if we take some sort of insulating material and we stick it in between the plates, what do you think that would do to the capacitance? Now, importantly, this is an insulating material. If you stick a conducting material in between these plates, you can't store any charge on them because the charge will just move through the conductor between the two plates. But if you have an insulating material that doesn't allow charge to easily move through it, this will still be a capacitor. What do you think that should do to the capacitance? Again, the ability to store charge. Okay, let's use a simulator and see if we can figure out the answers to those three questions. So this comes from the website that we worked with for the electric field mapping lab exercise, the fet.colorado.edu website. Here's the specific URL for this simulation, but you could also find it by going to FET, say play with the sims, and then go to the physics menu, the electricity and magnetism menu, and then choose the capacitor lab to play around with. So I've got this up on the screen in the background, and I'll bring that to the foreground now. So here's a situation where I have my two conducting plates, and right now they're separated by a certain distance, 10 millimeters. They have a plate area of 100 square millimeters, so they're 10 millimeters by 10 millimeters. And I've connected them to a battery over here, because again, the battery is going to act like a charge pump and pump the charge from one plate to another. So I don't see any charges on the plate right now, but if I notice, my potential difference for the battery is at 0 volts. If I increase the potential difference of the battery to be a normal, say, D cell, I would put it up to 1.5 volts, and notice in doing so, I now pump charge from what became the positive plate through the circuit and deposit it onto the negative plate. Now we'll talk much more in the next unit about what makes an electric circuit. So we don't need to worry too much about that right now, as long as you can understand that this connecting path will allow electrons to go from one plate to the other plate if the battery pushes them there. This is the positive end of the battery, so it would attract electrons, and then the negative end of the battery would push electrons away and onto this plate. But I cranked that voltage up fairly quickly. I'm going to do so a little more slowly now and hope that the screen capture catches this. So if I go back here, notice that when I increase the potential difference, some arrows are in there showing the direction of electron flow through this circuit. So I'm pumping charge, pumping charge, pumping charge, pumping charge. But when I get to a constant potential difference, I stop pumping charge and there's a fixed amount of charge on the plate. This wasn't one of the questions, but if I lowered the potential difference, say to be about half of what it was, notice that fewer charges exist on the plate. Again, potential difference we've defined as potential energy per charge. So essentially, if I decrease the potential difference across the battery, I'm decreasing the amount of work the battery will do in pumping charges, and that results in fewer charges being pumped through the system and fewer positive and negative charges ending up on the capacitor plates. So I'm just going to take this back up to 1.5 volts and then play around with the simulator to answer the 3 questions that we previously asked. The first one said, if you increase the plate area, what does that do to the capacitance of this thing, the ability to store charge? Well, I'm going to turn on a meter here that tells me what the capacitance is of this system, and right now it's 0.89 times 10 to the minus 13 farads. Farads is the unit of capacitance, named in honor of Michael Faraday, who was one of the pioneering scientists in the work in electricity and magnetism. So if we increase the plate area, what should that do? Well, increasing the plate area, notice increases the amount of real estate, if you will, that charges can occupy, and so you end up having more electrons removed from that plate and pumped onto the bottom plate, because if I pump one electron onto the bottom plate and then pump a second electron onto the bottom plate, it actually takes less energy to do that in this situation, because the first electron can move further away, and I'll be able to pump overall more charges onto that bottom negative plate because there's more space for those charges to spread out. More charge stored for the same potential difference, because I haven't changed anything about the battery, means a larger amount of capacitance, and you'll notice our meter here got maxed out in the process. If we take that area back down to what it was, 100 square millimeters, our capacitance has decreased in the process. The second question asks about changing the plate separation. Right now they're 10 millimeters apart in this. What's going to happen if we pull them further apart? Well, let's do that. Maybe. Well, let's not do that. Let's push them closer together and then pull them further apart. So I suppose it only allows us to adjust between the 5 millimeter mark and the 10 millimeter mark. So if we assume we were close together to start with, and they're storing a certain amount of charge, note that when we pull them further apart, the amount of charge that gets stored on those plates decreases, and the value that our capacitance meter over here reads decreases as well. Push them closer together, it increases. And one way you can think about this is, okay, I turn on the battery and that pumps one electron off of the positive plate. I'm thinking back to initially uncharged plates now. Pump one electron off the plate, send it through the circuit, deposit it down here on this plate. Pump the second electron through the circuit and deposit it on the plate. And it's repelled by the electron that's already on that plate, so it's a little bit harder to pump onto that plate than the first one was. However, that electron and all the subsequent electrons that I'm pumping onto this plate are helped by the attractive forces from the positive plate. So they're repelled by the negative forces on the negative plate. They're attracted by the positive charges on the positive plate, those positive charges are further away than the negative charges are, so the negative charges are going to win that battle ultimately. But this plate does help the charging of the lower plate because it's exerting attractive forces on the electrons that are being added to that bottom plate. So if I increase the separation between those two plates, I now decrease the amount of attractive force that newly arriving electrons on the bottom plate will feel. And when I do that, I actually decrease the overall number I can pump onto that plate before I have fully charged the capacitor in its current configuration. So that stores less charge, again, for the same potential difference. And that means the capacitance has decreased when I increase the separation. Got to go over here to this other tab to play around with inserting a dielectric material in here, and we'll again turn on a capacitance meter for the capacitance of this system. So I'm going to crank it back up to the 1.5 volts here, and notice we have the charges that we have stored on this thing. So I can take my dielectric, in this case, this material, this insulating material, and insert it into the space between the two plates and see what happens to the capacitance as a result. Well, notice right now the simulator is drawing positive and negative charges on this dielectric right on top of one another. But if we take this thing and insert it into the region in between those plates, notice that those charges become separated because this material will become polarized like we've seen in other situations. And that ends up exerting new attractive forces on the charges that are on either of these plates. So we've talked about pulling electrons off of the top plate and depositing them onto the bottom plate. Well, they're attracted by the positive charges on the positive plate, and they're also now attracted by the attractive forces due to that new material that we've inserted into the middle of this arrangement. And so that actually allows us to pump more electrons off of the top plate, add more electrons to the bottom plate, and the overall system stores more electric charge than it did when the dielectric was out of there. So here's the charge with the dielectric out, and as I insert the dielectric into here, more and more charge can be stored on that system, and you'll notice the capacitance reading on this capacitor meter goes up as well. Let's jump back to the slideshow and wrap this up. So what we saw is the capacitance increased when we increased the area of the plates, and that's not enough to establish this direct proportionality, but it turns out you can do this experiment in lab and show that as you increase the area of the plates, the capacitance goes up. As you increase the separation of the plates, the capacitance decreases, so those are inversely proportional to one another. And as you insert a dielectric material into the space in between those plates, the capacitance went up as well. The dielectric is typically written as a dielectric constant. This is the Greek letter kappa, looks a lot like a K, and we say that the capacitance is proportional to the dielectric constant. That's just a number that represents the electrical properties of the material you're inserting in there. Free space or empty space is 1. Air, which is nearly empty space, is pretty much 1, slightly greater than 1. But other materials have other values for their dielectric constants, and those can be looked up online or in most textbooks. So if we put those three things together, mathematically we say that the capacitance is proportional to the dielectric constant times the area divided by the distance between plates. And if I increase any of those factors, that will affect the capacitance. So if I put a dielectric in there and kappa gets bigger, capacitance goes up. If I make the plates bigger, I increase the area, capacitance goes up. If I move the plates further apart from one another, I increase the distance, capacitance goes down. And like we can do other places in physics, the way we turn this proportionality into an equality, an equal sign, is to introduce a constant. The constant in this case is given a special name. It's called the permittivity of free space, and it's written as this little epsilon 0 character, epsilon 0. has a value of 8.85 times 10 to the minus 12th coulombs squared per Newton meter squared, or 8.85 times 10 to the minus 12th farads per meter. And so you can equate these and see that the farad, the unit of capacitance, is equal to a coulomb squared per Newton meter as well. So one last slide and some comments connecting this to the laboratory mapping exercise that you did. From the lab, we saw that equipotential lines were parallel to the charged lines. So when you did the second mapping exercise and had the two silver lines that were parallel to one another, you found equipotential lines that were, or very nearly were, parallel to those charged lines on the carbon sheet. And that was a two-dimensional map. If you imagine that that was the side view of a three-dimensional system that consisted of two charged plates, those two charged plates would have a series of equipotential surfaces in between them. So I've tried to sketch that here. Here's my two charged plates, though I didn't sketch which charge was on which. And there would be this series of equipotential surfaces in between. So let's say the bottom plate was at a potential of 0 volts, and the top plate was at a potential of 10 volts. Well, then these surfaces, which are imaginary surfaces, they're in space, would represent places where the potential, electric potential, would be like 2 volts, 4 volts, 6 volts, 8 volts, and then finally 10 volts once you reached the top plate of this system. We've shown both in a tutorial work and in the lab questions, if you answered those follow-up questions, that electric field lines are perpendicular to equipotential surfaces. So here's the equipotential surfaces. The electric field lines have to pass through those perpendicularly. And the electric field within a capacitor, just like it does in any other charge arrangement, points from positive to negative. So here's a side view diagram of what this might look like. So here I'm looking at the end of a negatively charged plate. Here I'm looking at the end of a positively charged plate. The dashed lines represent the edges of those equipotential surfaces. And because the electric field passes through those equipotential surfaces perpendicularly, the electric field vectors point right to left from positive to negative, and they're parallel to each other. And if you have field lines that are parallel to each other, that tells you that the electric field is constant in strength in this region in between these two charged plates. It's not here on the edges. You might have noticed if you mapped that your equipotential lines do a little bit of curving here at the edge, but in the middle of this is a place where we have a fairly uniform electric field, and we will be working with that concept both here and when we talk about what capacitors do in electric circuits, and also what a capacitor would do to moving charges once we get to our electromagnetism unit in the third unit. This concludes the presentation on capacitors for the GP2 online lectures. Again, it's hoped that this is a helpful resource to those of you that are using them, and if you've noticed any errors in the presentation, I would appreciate you letting me know that. Thanks.